that. Hello, I'd like to talk to you today about the concept of the limiting reactant. So let's use the example of cooking. So 1 packet of muffin mix and 2 eggs and 1 cup of milk will make 12 muffins. How many muffins can we make with the following amounts of mix and eggs and milk? We can still make our 12 muffins. Limiting reactant is the muffin mix, because remember, only one packet gives you 12 muffins. But we still have excess eggs and excess milk. We can still make muffins. Still make 12 muffins. Again, if you go back to what it is, it's 1 to 2 to 1. One to 2 to 1. Can we still make our 12 muffins? Yep. 1 to 2 to 1. One to 2 to 1. Limiting reactant is those dozen of eggs, because there's one packet to 2 eggs. So once you use your 6, you're done. Okay. All right. So that's that example. We looked at little molecules. You could see before and after the reaction. If we had 3 nitrogen molecules or 6 atoms reacting with 3 hydrogen molecules, we're going to make 2 ammonias. But guess what? We're going to have 2 nitrogen molecules left over. That's the excess. So the limiting reactant in this example is the hydrogen. Okay? You just don't show the leftovers or the excess reactant in the chemical equation, okay? Because it just didn't take part in the reaction, that's all. All right, so when we write these balance, this would have been 3 into plus 3 hydrogens plus 2 ammonia, makes 2 ammonias. You just don't show the excess, what's called the excess, okay? What if we wanted to make cars? 8 car bodies, 48 tires, and 8 cars. We're going to have 16 tires left over, aren't we? Okay. So the limiting reactant or reagent is the reactant which produces the least amount of the product, or it limits the amount of product that can be produced. The others, what that's left over, is called the excess, and it's you don't ever see that in the equation. And the maximum amount of product produced by the reactant, the limiting reactant, is what's called the theoretical yield. And we can actually calculate that using mass-to-mass stoichiometry, just like we've been doing. And this is why we talk about limiting reactant now, is because now that we know how to do mass-to-mass stoichiometry, we can do theoretical yields. So I'm going to show you some examples and narrate them. However, I will have some examples worked for you again on Monday in addition to these. Okay, I don't want you to think these are just all you're going to listen to. All right, so what is the maximum mass of sulfur dioxide that can be produced by a reaction of 95.6 grams of carbon disulfide with 110 grams of oxygen? Carbon dioxide is also produced. So of course, we have to start off with a balanced chemical equation. And we have our balanced chemical equation. So the first thing we need to do is we need to take this 95.6 grams here and convert it to sulfur dioxide in mass. And then we need to take the 110 grams of oxygen and convert that to sulfur dioxide mass. So we're going to need to do 2 mass-to-mass stoichiometries. And we know our mole-to-mole ratios of carbon disulfide to sulfur dioxide and of oxygen to sulfur dioxide. So again, the first step is how much sulfur dioxide can be produced when 95.6 grams. Convert mass to moles, convert moles to moles of sulfur dioxide, and then finally to mass of sulfur dioxide. So we know that this reactant can produce 161 grams of sulfur dioxide. Well, we need to do the same process with the oxygen, the 110 grams of oxygen. So again, previously we had 95.6 grams of sulfur dioxide, convert to moles of sulfur dioxide, convert to mass. Then do the same thing with the other reactant, convert mass to moles, moles of A to moles of B, and then convert to mass. We get 147. So of these two reactants, which produced the least amount or limited the amount of the product produced? And you should say, correct, oxygen was. Okay, what's the theoretical yield? Well, theoretically, if we went into the lab room and actually did this reaction, theoretically, we should get 147 grams by calculation. Now, do we actually get 147? No, because no reactions go to completion 100% of the time. That means there's leftover oxygen present. Notice it's not listed, okay? And we can actually figure out of the mass of this react, how much mass is required to react with this, and subtract that from the 110, and we can figure out how much of the leftover is left. Okay? All right, let's look at another example. These are all work the same way. All right, the reaction between phosphorus and oxygen produces tetraphosphorus decaoxide. Determine the mass of tetraphosphorus decaoxide formed if we had 25 grams of phosphorus reacting with 50 grams of oxygen. Got to start off with that balanced chemical equation. We're going to convert this 25 grams of phosphorus to tetraphosphorus decaoxide. That's a 1-to-1 mole ratio. We're going to have to convert 50 grams of oxygen to the tetraphosphorus decaoxide, and that's a 5-to-1 ratio. Okay, same process. Mass to moles of A, mole of A to mole of B to mass of B, and we get mass. Do the same thing for the other reactant. Mass of A to mole of A to mole of B to mass of B, and we get that much. So which of these is the limited amount? Well, the 57.3, right? So that means phosphorus is the limiting reactant. So theoretically, this is the amount we should gain by this reaction. We can then take these two, combine this, and figure out how much oxygen, since oxygen's the excess, and figure out how much of the 50 reacted by figuring the same process. If we did the mass to mole to oxygen, this would be a 5-to-1, and then the 32, that's the mass that reacted, subtract it from 50, and that would be what would be left over. All right, why do we need to find the theoretical yield? Because in chemistry, we want to know what actual percent yield do we get. Because again, no reaction is 100% complete. So if you work at some place like Merck or Coors and you want to know your final product, how much are you going to get? You want to know how much you actually got and what your percent yield is. So it is in theory the idea of taking what you actually obtained from the reaction divided by what you calculated from the theoretical yield from the limiting reactant times 100. And the closer to 100 that you get, the better off your actual lab procedure was. So let's go back to that first example where we realized that the oxygen is the limiting reactant. That's our theoretical yield. Let's assume then we went and did the activity and we actually got 138 grams. Therefore, the percent yield is the actual divided by the theoretical, again, decided by the limiting reactant. That's a pretty good yield. So I would say that our lab procedure went pretty well. All right, I'll do another one. Here's the one with ammonia where we use the same masses of the reactants. So let's look at what happens when nitrogen reacts with hydrogen to produce ammonia. What if we had 5 grams of each? How do we determine what the limiting reactant would be? Same process, convert mass of reactant to the mass of the product using the molar masses and the mole to mole ratio, the mass of the reactant to mass of the product, mole to mole ratio, And then the last step, notice, is always the same. And then we see that nitrogen is the limiting reactant. And then that is our theoretical yield. If we wanted to figure out, again, how much hydrogen reacted and how much was left over, we would convert nitrogen to hydrogen and subtract that from the 5. Okay, again, that goes back to that other little picture that I showed you, that you ended up with some hydrogen left over and that's the excess. Yeah, that's why. Okay. All right, and that's an introduction, and you actually get to see some problems here, and then I'll work some more next week for you. All right.